We're going to talk fertilizer and nutrition. Fertilizer just seems to be like one of those weird words that is used like it's almost like a joke. People refer to it as BS and those kinds of things. But fertilizer and nutrition are incredibly important for turfgrass. We just have to get that right. In fact, if you don't get anything else right, fertilizer, especially nitrogen, is really important in terms of getting the right, setting the stage for plant health. Okay, so let's jump in and talk about that. We have these essential elements. There are 17 to 18 essential elements, kind of depending on what textbook you look at. There's a couple more listed on here, cobalt and nickel that you could include depending on, again, they're kind of newish in terms of being considered essential nutrients. In order for these things to be considered essential, the plant has to be able to have them in order to complete its life cycle, and there can be no substitute. Like for example, sodium is actually found at high levels in the soil and in the plants. And plants do use it as a nutrient, but plants can survive without it. I actually do hydroponic experiments where we're growing not in soil, we just are growing in liquid and adding all the nutrients. We can completely eliminate sodium, and the plants can substitute out for it just fine. But all the rest of these got to have them there, or the plants don't do well. Now, when we say it don't do well, they're weak, they're susceptible to pests, physiological stresses. We tend to have less growth, they tend to die out, and those kinds of things. So it's important. You can also have toxicities with these things too. You get them too high, that's a problem. In fact, that's a really serious problem that I see often. It's kind of interesting, as I mentioned in the soil testing video, that it's baffling that farmers understand the importance of measuring and doing soil testing. And in the urban environment, I really have a hard time getting people to do that. And if you just put on the same fertilizer year after year after year, you're going to actually not have a deficiency problem. You're going to potentially have a toxicity problem. All right, well, let's talk about the non-mineral elements. They actually weren't listed on that last slide. These are the hydrogen, oxygen, and carbon. They make up most of all organisms, including me and you, by weight, and plants as well. But we get these, or plants get these, from the water that they take up, as well as the carbon dioxide that comes in through the stomates of their leaves and is used for photosynthesis. So we get these guys from that. So we don't really have to fertilize. They just are kind of coming along free for the ride. We do see misguided folks peddling carbon fertilizer, for example, and it's just it's ludicrous. So not smart. We have these macronutrients. Again, we split up the mineral nutrients in two ways, as macronutrients and micronutrients. So let's talk about the macronutrients, and within the macronutrients, we split that up as primary and secondary. The primary nutrients are the nitrogen, we abbreviate as N, phosphorus, we abbreviate as P, and potassium, we abbreviate as K, because there's a K in the potassium, right? No, there's not, that, which is confusing, but leave it to the chemists, it's K. We won't bother explaining that, just trust us. Why are these primary? Is it because they exist at higher concentrations in the soil or in the plant? No. They do not. In fact, it's almost always we have more calcium, magnesium in a plant, which are set. Those are two of the secondary macronutrients. Than we do phosphorus. The reason these are primary macronutrients, it's all about how likely you are to have a deficiency. These three are by far the most commonly deficient. Nitrogen is actually number one by a long shot, and phosphorus and potassium are sort of, they're in a race for second place. But these three make up, well over 90% of the fertilizer that's sold worldwide. Now, by law, these three have to be listed. If you're selling something as fertilizer, by law, these three have to be listed on the bag, and they have to be listed in this order, like this on this bag here. So 17-3-17, means it's 17% nitrogen, it's 3% phosphorus, and 17% potassium. Okay, here's the weird part though. The phosphorus is expressed actually is not as P, but as P2O5, 2 phosphorus and 5 oxygens. And why? Well, because we thought back in the day when they made the fertilizer law that, you know, that's the way the phosphorus existed in the bag. It's not. It doesn't exist like that. It actually usually exists as phosphate, which is PO4. But anyway, bottom line is we're stuck with it. That's how it's represented. We're calibrated for it. Don't worry about it. You know, if we give a recommendation, you know, we factored that in already, so you don't really have to overthink it too much. However, you know, sometimes it is helpful to convert from P2O5 to P. So let's just talk about that for a second. So this bag of fertilizer, let's say it's a 100-pound bag. I have 3%. That means 3 pounds are P2O5. Now, if I wanted to convert that to P, and why would I want to do that? Well, you know, once that fertilizer hits the ground, we really don't ever talk about it in terms of P2O5 any longer. You know, we then, you know, like in plants or in the environmental world, and, you know, we are oftentimes doing math and we want to know the phosphorus level. And so you can convert that by multiplying it by 43.7%. So roughly you've got a little less than a pound and a half of actual P phosphorus in this 100-pound bag of fertilizer. Okay. Similarly, for potassium is expressed as K2O. It doesn't exist. You know, that's not what's in the bag, but that's how we express it because that's what we do, and we're stuck with it. And again, so this bag, if it's a 100-pound bag, it would be 17 pounds of K2O. And if I wanted to convert that to K or potassium, we would multiply by 83%. So that's, you know, roughly, I don't know, what is that? About 15 pounds of K. So there you go. Now, the secondary macronutrients, they're found in fairly large quantities. So these macronutrients, the NPK, as well as the calcium, magnesium, sulfur, we call them macronutrients because they're typically found at percent levels in the plant. So you might have phosphorus, for example, might be as low as like 0.2%, but it's still percent, even though it's, you know, 0.2. But, you know, it's somewhere north of 0.1%, and then maybe as high as even 3 or even up to 5%. Nitrogen, for example, is fairly commonly in those kind of numbers. So these 6 macronutrients tend to exist in those levels in the plant. These macronutrients are not very commonly deficient, or at least they weren't when we were classifying these things, right? Calcium and magnesium are still only rarely deficient. Those two are ubiquitous in the environment. The environment is loaded up. Every time you irrigate, you're putting on, you know, some free calcium and magnesium that comes with the water. Our soils tend to be high in these. Now, there are exceptions to that. So like in the Western United States where we're irrigating, we have soils that we call them calcareous soils, that they have this limestone that's natively high in calcium and magnesium. And I've done tons of studies, and you just don't get responses on turfgrass to these two. Now, there are some exceptions in some other crops like apples, but the turfgrass is very, very poorly responsive to these. Now, I'm not saying you don't ever get a response. If you have a really low pH soil, especially if it's a sandy soil, it's been leached, which means I've got water has been moving the nutrients out of it. You know, a low pH, yeah, you can get some calcium and magnesium deficiencies, but pretty rare. Sulfur used to be rare. It's increasingly more commonly deficient. In fact, I'm kind of to the point where I'm pretty routinely recommending sulfur to be applied. We'll talk more about those recommendations in a minute. Now, the micronutrients, again, not all of these were listed on that first slide. I've thrown in nickel and cobalt here because they are sort of recently been discovered to be essential. And again, it depends on what textbook you look at or what web page you look at, whether or not these guys are listed. But pretty unanimously, everybody agrees that zinc, manganese, iron, copper, boron, chloride, molybdenum are micronutrients, and then potentially also nickel and cobalt, depending on situation and the species. We see the abbreviations for each one of these. And these things tend to be found at part per million levels in the plant, in contrast to the macronutrients that are found at percent levels in the plant. So percent, if you think about that, that's parts per 100. If I have 1%, that means I have 1 part per 100. Parts per million is just a way of expressing concentration for things that are found at much lower concentration. So I've got a whole lot less zinc in the plant than I have nitrogen. And so we tend to talk about it in terms of the part per million. But these are found at fairly low concentrations. They're still needed. You still got to have them, even though you don't need much. The one exception to that might be chloride. Chloride is actually needed at fairly high levels. You might even broach into the percent levels with chloride. So, but essentially these things are micronutrients because they are needed in lower concentrations. Okay, moving on. Concentrations typically are below 1,000 parts per million. Chloride, again, is the exception. I've seen that as high as 2,000 parts per million. And we should note that cobalt is not universally accepted as an essential element. All right, let's talk about nitrogen for a minute. Most important one by far. Get that right, even if you don't get anything else right. Here's the nitrogen cycle. Some important things here. We're not going to go through this whole thing, but one of the things you see here is there are several loss mechanisms. Nitrogen is really subject to losses. We can lose it. You put on some fertilizer. We can get volatilization, which means nitrogen gas escapes into the atmosphere. We can convert the fertilizer to the nitrate form, which is really subject to leaching loss, which means water is pushing it out of the root zone or even over land, ends up in the surface water or the groundwater and not in my plants. We can also lose nitrate to the atmosphere through a process called the denitrification. And the bottom line is that means we're wasting fertilizer. Plus, I won't talk about it right now, but there's some environmental problems with losing that nitrogen. This is used typically in the greatest quantity of all the mineral nutrients, not counting carbon, hydrogen, oxygen, but of the mineral nutrients, it's the highest. It's included in lots of different things in the plant and lots of reactions. If it's deficient, we tend to have chlorosis, which means we get a lack of chlorophyll. The chlorophyll is what helps a plant be green in most cases. And so if I have a chlorophyll deficiency, the plant is less green. It typically is yellow. We get slow shoot and root growth. With excessive nitrogen, which is, I see a lot of that, people putting on too much. I get excessive shoot growth. You got lots of, I got to mow it a lot. And we also get very shallow rooting. It grows shoots at the expense of roots. All right. We also tend to have some interactions with some diseases. If I'm deficient in nitrogen, I'm more likely to have dollar spot or red thread disease. Excessive nitrogen, though, contributes to Pythium blight and brown patch. So that's another reason to try to get it right and hit that optimum area in the middle. So for application, now we have cool season grasses and warm season grasses. Cool season grasses, most common one is Kentucky bluegrass, tends to be in the northern part of the United States. We would typically say we want about 3 to 5 pounds per 1,000 square feet of nitrogen per, again, 3 to 5 pounds of nitrogen per 1,000 square feet. So, if I'm in a sandy soil that's more prone to leaching, or I'm in other scenarios where I'm more likely to lose the nitrogen, I might want to be higher on that scale. If I am I'm sports turf, golf. We tend to be a little bit higher, closer to that 5 pound mark. Although I see people much higher than that, which isn't good. But for the most homeowners, most applications, 3 pounds is enough. I can just do that and it'd be great. I kind of like to see about a 1/3, 2/3, about 2/3 applied in the fall. I want most of it in the fall. It actually helps me put the grass to bed for the winter really well. And it makes huge dividends in the spring. And that's really when a plant is just really growing roots, is in the fall. Unfortunately, most people are sort of done with their lawns in the fall. They're like ready to go skiing or whatever. And they aren't thinking about, getting out there. In the springtime, we all want to go out and get our garden going and we're excited. And, and then, we kind of neglect things in the fall. Well, we really need the fertilizer, especially the nitrogen, in the fall. And so I like this 1/3, 2/3 rule. So if I'm going to put on 3 pounds, I'm going to put on about a pound of nitrogen in the spring and about 2 in the fall. Timing wise, it kind of depends on where you're at, but like Provo, Utah, I'm typically going to put that third down, as soon as it starts greening up in the spring. I could wait, I've got a month or 6 weeks even of flexibility of when I need to get that nitrogen down. In the fall, I want to put it down early enough so it's going to do some good. So I typically am putting it down, like the first to the middle part of September. You could go as early as late August. You could go as late as, September or even October. But you really need to get it on there. Now, I like to use about at least half of what I'm putting on as a slow control release, upwards of 3/4 of it, with the rest as a quick release. And the reason is I want a little shot in the arm. I need to get some nitrogen in the system, and the quick release is going to do that for me. But the slow release then meters out nitrogen slowly over time, kind of helps spoon feed that nitrogen. And it results in less mowing. It results in better root growth. It's just better all around. So that's a good blend to do something in that neighborhood. So what I'm saying is, let's just say I'm going to do 50-50. 50% slow control, 50% is quick release. So if I'm, let's say I'm doing my fall application, I'm going to put 2 pounds of nitrogen down in the fall. So what I'm saying is 1 pound would go on as a slow release, 1 pound would go on as quick release. I'd probably blend them together and apply it at the same time, but that's the mixture I like. I think that's a really good formula. It works in almost every situation. Now, when we talk about quick release, we're talking typically about urea or ammonium sulfate. If I need sulfur, which is fairly common, this is how I like to get my sulfur on, is using this product. If I don't need sulfur, I can usually buy urea cheaper, and I'll use that. For the slow and control release, there's actually lots of products. In fact, there's more quick release products than that. Those are just the 2 most common. With the slow release, again, a whole bunch of products. I'll show you a picture in a minute, but polymer coated is usually what I use for dry applications. If I'm putting down a liquid, there's several choices that we could use, like methylene urea, for example. We can also just add regular urea or even some ammonium form and just add some inhibitors. You got to use the right inhibitor and understand how that works, but that's another option for us to slow down and spoon feed that nitrogen. Super important. This is probably the most important slide I'm showing you today. Get this right, and we can forgive a lot of other sins in the taking care of the grass. Now, warm season grasses, these are the ones that are growing down south, Bermuda grass being the most common. The general rule is about 1 pound of nitrogen per every 1,000 square feet for every month of growth. So if I've got a 9-month season, what we're saying is kind of upwards of 9 pounds. Now that's a little high. I can get away with less of that as long as I'm using some slow control release stuff. In fact, I've even cut that back as much as half and been just fine. But that's sort of the rule of thumb that gets promoted by the folks down south, is 1 pound per 1,000 square feet for every month of growth. Now, will hear folks though say that if I have the sandy soils that are prone to leaching and are or I've got some soils that are prone to denitrification, they might actually require more than 1 pound. I'm not a real big fan of that. I think that I can manage that using the right sources and not have to apply that much nitrogen. Now, we have a situation where we overseed turf. What do I mean by that? That means typically I'm in the south, warm season area. I'm growing something like Bermuda grass, a C4 warm season grass. But let's say I'm the Phoenix Cardinals, and I've got my Bermuda grass field. Well, by the end of the season, it's starting to turn brown. It's going dormant on me. And nobody likes that. You know, the crazies who have to have things perfect for football, they want it green. And so we'll overseed it with a cool season grass. Perennial ryegrass is the most common by far. And so now I'm growing grass again. And so in that situation, we're going to favor the permanent warm season turf. When the warm season is dormant, we want to apply just enough nitrogen to prevent chlorosis for the cool season turf. We don't need much, but we probably do need a little bit. All right, I've mentioned urea, most commonly sold fertilizer in the world. Once that urea hits the ground, it's converted to ammonium within a few days. Then that, within a couple of weeks, is converted to nitrate. Now the plant can take up both ammonium and nitrate. It'll take them, either one of them up. But because of this process, most of the plant take up is in the form of nitrate. Now, urea is pretty inexpensive. It's easy to work with. It doesn't cake up very badly. It has a low burn potential, but it is very susceptible to loss. If you go out there and apply it and it's a hot day, especially if it's humid and the wind's blowing, I'm going to lose some of it to volatilization. We see numbers commonly at 10 to 20% loss levels. So that's kind of high. If I go out there and throw a little water on it with the irrigation system, I've greatly reduced it. I'm still going to lose some, maybe 5%, but it surely helps. Now, ammonium and nitrate-based fertilizers often have higher burn potential. Not always, that's kind of an oversimplification, but it is a concern. It would be important, though, to say so like a urea or ammonium sulfate, I mentioned that one. Ammonium nitrate used to be common. It's kind of hard to get that anymore. There are some other nitrate fertilizers, but these are often what we call water soluble nitrogen sources. And that means they're quick release. These slow release forms are insoluble, what we call water insoluble nitrogen. So here's some examples, like here's Osmocote. It's got 40% nitrogen in it. It's got this polymer coating, and it slowly meters out the nutrients over time. IBDU is a slow release because it's a long chain polymer that kind of breaks down. Same thing with urea formaldehyde. It's just this really long polymer that's got a bunch of nitrogen in it, and as the microbes or the chemical breakdown happens, it releases nitrogen in the soil. Oxyamide is similar. Sulfur coated urea is more like this Osmocote. This has got a polymer coating. This has got an elemental sulfur coating. And then here's another one, Procoat, which is another coated product. These water insoluble nitrogens tend to cost more, but they help us spoon feed, and they typically are worth it. It greatly reduces burn potential. The spoon feeding, again, is very advantageous. It avoids these flushes of growth. If I go out there and put on 2 pounds of nitrogen and you got any kind of warm temperatures at all, this is going to grow like crazy. And that's not good. It's actually can harm the plants. The roots don't grow very well. Oftentimes we can't get in there with a mower quickly enough, and you end up scalping it because you should never take off more than 1/3 of the shoot. But if it's growing super fast, you're more likely to do that. One of the great advantages that I love about these things is they're less likely to leach or have lateral flow or volatilization, these losses to the atmosphere or to the water. It's important that we're environmentally conscious. It's important that we're efficient, that we don't be wasteful. And so I think it's wise to put on, some nitrogen in these forms. All right, let's switch gears. Phosphorus. Again, phosphorus is not very commonly deficient in turfgrass. It's way more commonly deficient in a lot of other things, crop plants. Turfgrass has just really got a very fibrous root system. So once the plants get established, it's really efficient at getting phosphorus. Now, during establishment, not so much. I mean, it's important, like if we're seeding or putting down sod, it's important to have a nice shot of phosphorus there for us. All kinds of uses, energy transfer and storage is one of the most important things. We talk about that as being one of the most important things as far as phosphorus use. If we get deficiencies, we get all kinds of problems listed here. Excess phosphorus, though, I see that frankly more commonly. And it really doesn't, having extra isn't helpful. It favors annual bluegrass. It's an environmental problem. And then I would say, even though we don't have a lot of evidence of it in turfgrass, certainly in most other species, we see too much phosphorus actually creates a toxicity by creating deficiencies of some of the micronutrients like zinc and manganese. It's really good to put this stuff on at establishment. I like to put on a heavy load when I'm getting ready to, till in the soil before I sod or seed. Phosphorus isn't very mobile, so this really becomes the best time to apply to kind of get it worked down into the soil. The roots are, like I said, very efficient at taking up. Now, potassium. It's actually not part of any biochemical compounds inside the plant, but it's a cofactor in many reactions. And it's part of several major cellular constituents. It's really important, especially for water relations in a plant. We rarely see deficiencies. It does reduce photosynthesis, though. We get reduced carbohydrate production, reduced stress tolerance to heat, drought, cold, and wear. So it's important. It's not really visible sometimes, but especially if I'm getting a lot of stress on the grass, like in a high traffic area of a golf course or something, it's important that this stuff potassium is rich in the soil. All right, let's talk about these secondary microbes now. Sulfur deficiency results in chlorosis, kind of similar to nitrogen. Again, it's often misdiagnosed as nitrogen. We see a response to sulfur increase with sand content increase and organic matter decrease. So the soil test for sulfur is actually not very good. Like phosphorus and potassium, soil test is really pretty good. Nitrogen, not so much, because nitrogen's so transient in the soil. Sulfur, not so much, but for a different reason. It's just the sulfur doesn't correlate very well. But what does correlate is how much sand content. Sandier soils tend to be more responsive to sulfur, but the higher the organic matter, the less likely. So what's the bottom line? It's like, well, if I'm less than like 1%, 2%, I probably should be putting some sulfur down. The higher the percent, the less likely you are to get, the less important it is to put it on. I still kind of like to get it on there, though, once in a while. Maybe not every time. We can get sulfur through irrigation water or even rainwater. Now, the calcium and magnesium, again, deficiencies are very rare. It's most likely on these highly leached acid sands. Here's the thing, though. We use limestone to raise the pH. Well, limestone contains calcium and or magnesium. So a lot of times, just managing the pH will give me enough calcium and magnesium for my nutrition, kind of getting double duty out of the limestone. Sometimes these deficiencies of magnesium look like nitrogen and or iron. Again, micronutrients, pretty rare. Iron is the most commonly one that's visually deficient, although I would tell you that we sometimes see a visual response, but with no real impact for growth. This is going to happen most commonly in alkaline soils. For most of these nutrients, chloride and molybdenum will be an exception. Now with iron, it's really a problem. At high pH alkaline soils, like we have in the Western United States typically, where we have low rainfall, it's very insoluble at high pH. Fortunately, the plants have adapted to that, and they make it soluble. They actually exude chemicals or protons that'll dissolve it. So that's kind of cool. Deficiencies again occur at that high pH though, and it looks like we misspelled pH. Sorry about that. It's not very mobile in the plant. Foliar applications do work, but they take repeated application. I'll tell you that, like for a football game that's going to be on TV or golf, we'll spray with an iron product a few days before the game and get a nice green up. We don't, again, it doesn't really seem to affect the growth other than we just looks a little better for TV. It's important to irrigate properly with these things. And most importantly is make sure we plant cultivars that are suitable for alkaline soils. Now, zinc and manganese, I'm not going to go all through that again, but they have pretty similar issues. Chloride, again, deficiencies are really rare. We typically have chloride in the soil and in the water. It's most common in the sandy soils. It's got deficiencies that are present when managers believe chloride is bad. So what does that mean? Well, what it means is that I see a bunch of people bad-mouthing chloride. And so, like, for example, potassium, the most commonly sold potassium fertilizer is potassium chloride, which is also called potash. But sometimes these salesmen of other products will convince people that chloride is bad. They'll call plants chlorophobes. Well, the reality is the plant's got to have some chloride. We just don't want too much. Too much is not good. I'll admit that. But if you just completely back away and you don't have any chloride in your system, like typically that's non-irrigated. If I'm irrigating, I'm probably getting enough chloride for my needs. So let's say I'm in, Georgia, I'm not irrigating. I don't have a lot of chloride in the system. I'm not near the coast where, we get chloride in the sea spray. You can get some chloride deficiencies in this case, especially if I'm removing the clippings and, putting a lot of pressure on that thing. It is important to realize that chloride fertilizers do have high salt content, so we've got to keep an eye on that. But again, chloride is essential. Let's talk about solubility for a minute. Actually, I didn't really talk about boron or nickel or cobalt. There's very, very rarely deficient. I do see deficiencies. I trust my soil test though. And, if it says I'm pretty low, which is usually on these really sandy soils, like we have in USGA golf greens or tee boxes or STMA spec, not STMA, sorry, ASTM spec sand-based sports fields. They're more likely to have some of these deficiencies, like with the boron. So if you need to, reach out on that. Again, solubility. This is important to understand how these nutrients behave. Soluble anions, soluble chloride, and mostly soluble sulfate, borate, and molybdate. These guys readily leach through the soil. Now, phosphorus is an anion too. So you'd say, well, that should be leaching through the soil, but it's much less soluble. So these anions, I failed to say this, like chloride, sulfate, borate, molybdate, those are all anions, and they're negatively charged. That's what that means. It's an ion that's charged and it's negative. Well, the soil is also negative, so they repel each other. So when the water comes through, they move really easily because the soil is not hanging on to them. So the contrast is phosphorus is also an anion, but it doesn't really move, like I said before. But the reason doesn't have anything to do with anion, but what it does have to do with is that it's not very soluble. And so it tends to just kind of form a rock sitting there in the soil and doesn't move anywhere. Now, the soluble cations, ammonium, potassium, and mostly soluble calcium, magnesium, and sodium, these can be leached, but they do it at a slower rate because they're cations, which means they're positively charged. So the negatively charged soil attracts that positively charged ion, and so it's less likely to move. It'll move, but it's slower. These things are also attracted to the organic matter. And most of the negative charges in the soil itself are on the clay, even though, silt and sand do have some, but pretty low. These less soluble cations, zinc, iron, manganese, copper, nickel, and cobalt, are attracted to the CEC. Their movement is governed by precipitation. So that's what's important to realize. Well, unless you want your cat being in charge of your fertilizer plan, I'd say it's important to make a plan. Again, it starts with soil testing, understanding these nutrients. I'll be honest with you, even though I talked about cobalt, the reality is 99% of what I am recommending in the urban environment is just nitrogen and maybe sulfur. Most of us have built up our phosphorus, potassium at such high levels that I'm not going to need any, in 2 lifetimes. And the micronutrients are likely in good shape and are pretty rarely deficient. And so it's pretty common for me just to put on nitrogen and sulfur. And that's oftentimes my main fertilizer plan based on soil testing and these principles. Well, I hope you enjoyed that. I hope you learned something and it's helpful for you. Go Cats.